of course, to have a headset and a microphone that works. For the presentation, I will mute your microphone so that we don't hear other noise. So, Carlo, feel free to start when you want. Thanks again very much in the name of IIFC to take times to present and prepare this webinar today. Thanks again, and as you want to start the webinar.
Okay, thank you very much, Emmanuel. Good afternoon, everybody. My name is Carlo Paulotto, as was told by Emmanuel, and I'm a civil engineering. In the last decade, my main interest was the application of FRP to civil engineering. This presentation will be focused on the experience gained by Acciona, that is a Spanish contractor, on the application of FRP to bridges in the last decade. My presentation is divided in three main blocks. First block is an introduction and is devoted to explain why we think FRP materials are good for a bridge construction. The second block is devoted to present the method, the design method we follow to design our FRP girder bridges. And the third block is devoted to present the evolution of the manufacture of our manufacture process. And finally, there is some slides devoted to the main conclusion that can be drawn from our experience. Before moving to the first block, let me spend a couple of slides just to be sure that everybody is on the same page. If you imagine to cut out a piece of the wall of our FRP girder and look this little piece through a lens, what we realize is that our wall is formed by a set of lamina stacked one on top of the other. And if you look at this element closer, you will realize that each lamina is formed by a series of fibers, aligned fiber, embedded in matrix. Okay? It's generally a polymeric matrix. You can realize that the mechanical behavior of this lamina is very different in the direction of the fiber than in the transversal direction. That is, the lamina is mechanically highly orthotropic. There are many ways to manufacture FRP laminates, but all the process share the same four steps. Impregnation, this means the dry fabric is wetted by the resin. The layup step, this is the step in which the lamina are put one on top of the other with a predetermined orientation. The consolidation step is the step at which the air trapped in the laminate is squeezed out from the laminate, and the solidification, there is the step in which the polymeric matrix gets solid. Here I have put two examples of two manufacturing process. On the left, you have a wet layup process. It's very simple, in which you put a layer of resin on a mold, generally a steel mold, or then you put dry fabric on top of the resin, and then with the roller you push the dry fabric against the epoxy or resin layer in generally, so to soft. In this way you can get the dry fabric wet and at the same time consolidated the laminate, and then you can supply heat to the laminate to cure the resin. In this way the resin gets solid. A little bit more complicated process is resin infusion, and then I will show you how we use this process to manufacture girders. In this process you have a steel mold, and on top of a steel mold you start piling up dry fabric. Then you cover the dry fabric with a plastic sheet that is called vacuum bag, and you seal this plastic sheet against the mold. So this vacuum bag is airtight. Then you can connect this bag to a vacuum pump and to a resin tank. If you open the valve that connects the bag to the vacuum pump, you practically make a vacuum in this bag, and you consolidate the dry fabric. Then, if you open the valve that connects the resin tank to the bag, resin starts flow into the bag and impregnate all the dry fabric. At the end, you supply heat to the laminate to consolidate it. After this short introduction, let's move to the first block of my presentation. It is devoted, as I remember you, to why we think FRP materials are good for bridge construction. First reason we think FRP are good for bridge construction is that FRPs can curb maintenance cost of bridges. The maintenance costs of bridge stocks is very high. According to the Federal Highway Administration, the corrosion cost of a highway bridge only is around $8.3 billion a year, and the indirect costs are 10 times this sum. So you realize that this is a huge amount of money. And the main reason of this cost is steel corrosion. Since FRP do not suffer from galvanic corrosion, they offer a good chance to curb maintenance costs of bridge stocks. This is appealing not only for government that presently are fighting to keep under control their budget, but also for contractors, because nowadays large infrastructure contracts are often bid as design, construction and exploitation projects. This means that you not only design and construct the infrastructure, but you also you have to exploit it. This means that you have to maintain the structure for 20, 30 years before giving the infrastructure back to the government. So even for a private company nowadays, is very interesting to be able to curb maintenance costs of infrastructure. The second reason we think FRP are good for bridges is FRP can reduce the weights of bridge girders. Generally as contractor, we not always have our work site in urbanized area. Sometimes our work site are in area with a very challenging logistics, in which communications are very difficult, and where you don't have very powerful tools, if you want. Here is two examples. For example, the first step, the picture on the left is, for example, a bridge you encounter in central Gabon, where we operate there. So you can realize that you cannot cross this kind of bridges with very heavy materials. And often in this area, you don't have at your disposal a very powerful crane to install bridges, but often you use, for example, an excavator as crane. So if we can have a very light structure, this simplify transportation and installation in this area. Here you have an example of a comparison between the weight of a 14-meter long reinforced concrete girder that it weighs around 30 tons, and a 14-meter long FRP girder we manufacture that weighs around 4 tons. So there's a huge difference that can simplify enormously transportation and installation in this area. The third reason to use FRP in bridges is that FRPs can speed up bridge construction process. Here on the left is a picture that more or less represents what I have my ideal work site when I was a civil engineering student. Open spaces, big machines. This was like to be a pioneer in the Wild West. But actually, when I start working in a construction company, I realized that often work sites are very different. Generally are in the middle of very urbanized area. This is an example of one of these work sites. This is a picture of the construction phase of Viaducto Bicentenario in the center of Mexico City. The work site is this narrow strip in the middle of this freeway. So you realize that you don't have a lot of space to build your infrastructure. And another thing you think when you are a student, and people will be grateful to you because you are building a new infrastructure for them. But the sad reality is that people actually hate you because they see you as an obstacle between their house and their workplace. So if you actually are able to shorten the duration of the work site, you will really make them happy. So since FRP foster prefabrication, they are able to reduce the impact of the construction activity on people's life. This is very important, especially for politicians. Let's move to the second part of the presentation that is devoted to present the way we normally design our FRP bridges. The first step is this material selection. Generally, we select material depending on the stress state existing in the different parts of the bridge. Here you can see a cross-section of one of our bridges. This is a cross-section at the abutment, because you see here the the supports and the cross-section of the diaphragm at the supports. But you can see from this picture that in our case, bottom flange laminate is mainly made by carbon fiber at 0 degrees, while the top flange laminate is mainly glass fiber at 0 degrees, and the web laminate is mainly manufactured using glass fiber at plus minus 45. The reason of this orientation is obvious. Top flange and bottom flange resist mainly tensile and compression stresses induced by bending, so their direction is the fibers are aligned in the direction of the bridge, while the web resists mainly shear stresses, and for the reason fibers are oriented mainly to in the plus minus 45. The design of the FRP bridges is mainly conditioned by the service limit state, and especially by the long-term seg of the bridge. The reason of this behavior is that FRP exhibit a pronounced viscoelastic behavior. Here you can see two diagrams taken from the Eurocomp design code. And on the left, you can see a graph in which you have the strain versus time. If you load, for example, a FRP element and you keep the load constant, you have an instantaneous deformation. Then, with time, you develop a secondary creep. And then, if the stress is very high, you have a tertiary creep, or so you get a creep failure. So the first step in designing FRP girder is to limit stress induced by sustained load in order to avoid creep failure. And the second step, you have to have sufficiently low stress induced by sustained load. The second step, you should take into account the apparent reduction in Young modulus due to the creep. Here you have an example. For example, you have here on the ordinate, you have the ratio between the apparent Young modulus and the initial modulus, and here the time. And you see how it's different, the behavior of a unidirectional laminate in tension and unidirectional laminate in shear. You can understand very well this difference if you think that the laminate behavior in tension is dominated by the fiber, while the mechanical behavior of AUD laminate in shear is dominated by the matrix. So, taking into account this difference in behavior between tension, shear, and then you can conservatively assume that the compression behavior follow the curve of shear behavior, you can understand why in this cross section we select reinforced concrete to resist compression forces. We don't think it's a good idea to resist compression forces using laminates, so we prefer resist compression forces using concrete and using FRP to resist tensile stresses and shear stresses in this region. Here you have a top flange of FRP that is mainly made of glass, cheap glass fiber, and it will work only during the installation phase before casting the concrete deck on the bridge. Once we have selected the manufacturing process and the basic material, that is resin and fiber, we go on with our design process, performing a reduced version of the pyramid test of the aerospace industry. So what we do, once we have selected the matrix, the fiber, and the manufacturing process, we manufacture coupons, specimens, and we test them. You can see why we test them. In this way, we characterize the mechanical behavior of the lamina. Here you can see some samples that we tested for UD, I think it was a UD carbon fiber fabric. You see the specimens we tested in tension in the 0 direction. The specimen we tested in tension in the 19 direction. This is the specimen we tested in compression. This is the specimen we tested in shear. And these are the specimens we tested in with the shore beam tests. So you can realize that due to the nature of the lamina, that is, to the fact that the lamina is highly orthotropic, to characterize the single lamina, you need to perform a lot of tests. Generally, we don't perform tests at element level, that is, at the laminate level, because it's very difficult to perform tests on laminates that have thickness of the order of centimeters. Imagine how difficult can be testing in tension a thick laminate of 1 centimeter, finding a proper way to grip the specimen. It's very difficult to transfer forces from the machine head to the specimen, avoiding damaging the specimen at the grip. So for this reason, generally we don't perform tests at laminate level, but we evaluate this property numerically. Sometimes we perform tests at subcomponents level. For example, we perform tests at the shear connector between the FRP girders and the reinforced concrete deck if we change the typology of shear connector. So if we don't do this, we test only once. And then we have tested in the past components. And for components, we mean girder. We perform real scale tests on FRP girder to prove that the concept works. You don't need to perform this test for each new bridge if you don't change the typology of bridge. And then the last test is the full-scale test that we always perform because it's mandatory. Forget to tell you that if it's not necessary to perform these tests at coupon level each time you need to design a new bridge if you don't change the material you use and the process you follow to manufacture your laminate. As I told you, the following step is starting from the property of the lamina we evaluated experimentally. We select a certain percentage of orientation of fiber. So we select the architecture of the laminates depending of the part of the state, depending on the state of stress state exists in different parts of the girder, and we evaluate the laminate property numerically. We generally use a software called CADEC that was developed. It's a freeware, and has been created and maintained by Professor Eva Barbero of West Virginia University. And what we do the first check with this property, laminate property. We perform the first check of the bridge by hand calculation using the Timoshenko beam theory. If everything is okay, we start simulating bridge, implementing a finite element model of the bridge. And to do this, we generally use ANSYS software. To simulate laminate, we generally use layered elements like shell 99 and shell 93. These like shell 99. These elements are layered elements. This means that they are defining the property of each lamina of the laminate. The ANSYS automatically evaluate the stiffness matrix of the material, and you can apply failure criteria lamina by lamina automatically by asking to do this to the software. To simulate a sandwich structure, we use the element shell 91 because for shell elements the classical lamination theory doesn't apply. As I told you, for each time we change typology of the girder, we have performed a real scale test of the girder, and we have compared the experimental result with the result of finite element simulation in order to evaluate, to assess if the finite element model is able to represent the actual behavior of the FRP girders. This is a test of one of our girders performed at the European Laboratory for Structural Assessment in Ispra, Italy. In this case, for example, you see that the girder was submitted to 3 cycles up to the service load and 3 cycles up to ultimate level load. This is the displacement, a midspan of the girder. You see this is the LVDT number 16. Position in the center of the cross section at the midspan. And you can see that there is a good agreement between the numerical model and the actual behavior of the girder. Let's see. We have checked that there is a good agreement in terms of displacement. Let's check if there is a good agreement in terms of longitudinal strain. So we applied strain gauges, a lot of strain gauges, to the girder. You see there is all the rosette here and strain gauges. And we are looking at the strain gauges applied at the midspan, at the bottom of the girder, along its longitudinal axis. Once again, you see there is a good agreement between the numerical and experimental behavior of the girder. And after have checked the strain in longitudinal direction, we check if there is a good agreement between angular deformation. To do that, we can check the rosette positioned here, close one of the supports. And you see there is still a good agreement between the numerical behavior and the experimental behavior of the girder at service limit state, at ultimate limit states. After these three tests, after these 3 cycles at service limit state and 3 cycles at ultimate limit states, the girder was finally submitted to increasing load up to failure. This is failure. See, there is the behavior of the girder is essentially linear elastic. You have a little bit of nonlinear behavior here, but it's essentially elastic. And now, try to compare again the displacement at midspan, the experimental results with the numerical result. And there is still a reasonable good agreement, taking into account that at failure the girder is experiencing some inelastic behavior and the model is elastic. You see that even in this case, there is still good agreement between the physical and numerical results in terms of displacement. The strain gauge at midspan, at the bottom of the girder, you can see there is still a good agreement between the numerical and experimental values. But if you look at what happened, the strains close to the abutment, you see that the numerical model is not able to represent the physical behavior of the laminate. And this is obvious because the model we use is an elastic model, and the failure was localized close to one of the supports. So in this area, the model is not able to capture the actual behavior of the girders. But I need to say this is not a problem because so far we design laminate for first play failure. So actually we not are interested to capture this very inelastic behavior of the girders. As I told you, actually the design is dominated by the service limit states, not by the ultimate limit states. You have enough reserve of resistance. If we go back here, you see that actually you have the failure of the laminate at a load level of 2,500 kilonewton, and the sign level at ultimate limit state that I show you is 1,000, more or less 1,500 tons. This is the ultimate limit state, and this is actually the load level where we observed the failure of the girder, so there is enough servo strength. Let's move to the third part of my presentation. In this third part, I would like to illustrate to you how the manufacturing process, our manufacturing process, has evolved in the last decade. The first FRP girder bridge we built it in the north of Spain, Asturias, in 2004, and it was a continuous girder bridge on the 3 intermediate supports. The span were 10, 13, 13, 10, so for a total length of 46 meters. We adopted a closed section girder, aerospace carbon fiber prepreg, and laminates were consolidated by vacuum bagging. You see, this is a picture of this bridge, and you see in this case one step of the manufacturing process. In this case, we are applying carbon fiber prepreg on stay-in-place mold made by polyurethane. Here are some pictures of the installation of the bridge. You see this is a 46 meter long girder that is positioned in one shot on the 3 support. Since the girder is made by carbon, only carbon, is extremely light. The girder weight per unit length is only 1 kilonewton per meter. The girders were manufactured in trunks, in 2 trunks here in Madrid, and were transported to the site in north of Spain and joined in situ. You see here another girder just joined and ready to be put in place. To join them at site, we use wet layup. To speed up the installation process, we use stay-in-place formwork, you can see here, that were already connected to the girder before installing the girder. So once you put the girders on the supports, you can immediately start and you put the reinforcement in place. You can start pouring concrete immediately. Due to all this innovation, the 340 meter long girders were installed in only 3 hours. This was very successful to shorten the installation time of the bridge. Okay, the following bridge actually were 2 Queen's bridges we built in 2007 on the outskirts of Madrid. And we apply a set of modification to our manufacturing process, taking into account the lesson learned during the first application. As I told you, for the third application, we use a closed-section girders with trapezoidal cross-section. This is very good from a static point of view, but this obliges you to use a stay-in-place mold. The stay-in-place mold is represented here by this polyurethane mold. This means that you lose, for each of the girders, you lose the mold. And this increases very much the costs of these girders. For this reason, when we start designing the second and the third bridge, we decided to go for an open section. And why for an open section? Because in this case, you can use a steel mold that can be reused for each of the girders. So you can use a couple of girder to manufacture all the, you can use a couple of molds to manufacture all the girders. In this case, we use 2 molds to manufacture the 24 girders of these 2 bridges. And another modification we adopted was passing from continuous girder to simple supported span. The reason of this is that, as I told you, normally composite material don't work very well in compression. So in the area with negative moment, the detailings of the solution start to be a little bit complicated. So to avoid this problem, we move to a simple supported solution. These girders are simply supported on the column and the abutment. A third modification we use for this bridge is that here, in this first demonstrator, if you want, we use, as I told you, aerospace carbon fiber prepreg. Aerospace carbon fiber prepreg is very expensive. It's very expensive because it's thought to be used for very different requirements that are normally the normal requirements of civil engineering. So to try to reduce costs, what we did, and we produced our prepreg in-house. I mean, we took dry fabric, we bought a machine to impregnate the fabric, and we manufacture our prepreg. And you see here, people is stacking prepreg fabric on the steel mold. Another modification. The previous bridge was completely made by carbon fiber. Carbon fiber is very expensive when compared to glass fiber. So for this new bridge, we decided to use a carbon fiber on only specific part of the bridge, not all the bridge in carbon fiber, because often it's not necessary. In this way, we were able to reduce very much the cost of the FRP girders. Since we use glass and carbon and not full carbon girder, you have to pay a little bit in terms of weight. You see, we pass from 1 kilonewton per meter to 3.5 kilonewton per meter. But even in this case, you can see that it was possible to install the girder using a simple truck crane. And also in this case, we used stay-in-place formwork. to speed up the construction process. These templates formwork are essentially glass fiber polyurethane sandwiches structure. And this is very interesting. This is, let's move to another example of FRP bridge. This is a pedestrian bridge we built in 2010 here in Madrid. And this example is very important to explain how it's important to have a good communication between the architects and the structural engineer at the early stage of project. The idea, generally the architect is fascinated by FRPs for their capability to create innovative shapes and for the quality of surfaces. In this case, for example, the architect was very interested by creating a contrast between the reinforced concrete and composite material surfaces. The example he gave us was that in his mind, this FRP pedestrian bridge should resemble Eva, is of the Pixar cartoon, with shining white apple shining, and the ancient reinforced concrete pedestrian bridge that was positioned here could resemble Wall, this rusty robot. This was the main idea of the architect. But from a structural point of view, there are other things that are important from a structural engineer. For example, the depth of the girder. In this case, this is a 42 meter long girder, and the depth of the cross section is only 1.2 meter. We try to convince the architect that 1.2 meter is too low for such a long girder, FRP girder, but we were not able to convince him to increase the depth because he was very interested in the very slender shape of the girder. So we were obliged to keep the depth of the girder at this level. Another very complicated thing is that, as I explained you at the beginning of this presentation, is that composite material generally don't work very well under sustained load. But in this case, for example, the architectural choice was to cover the internal part of this FRP girder with reinforced concrete tiles that were prefabricated. These tiles do not dissipate to the resistance mechanism of the structure. They represent only dead weight on the structure. As we fail, to say that we fail to try to communicate the architects the negative effect the dead load has or have on the composite material. But at the end, we were unsuccessful. We were not able to modify this situation. So we designed this structure with a very small depth for the length and with a very disfavorable ratio between live load and sustained load. We had a very tight schedule at the time we had to manufacture this pedestrian bridge. So to speed up the manufacturing process, we decided to change manufacturing process. We changed from wet layup to resin infusion. You see here a step of the lamination process. You see people are deploying carbon fiber fabric, dry fabric on the mold. And you see here a picture of the girder just before injecting resin into the vacuum bag. You see here the vacuum bag. Here you see the thermocouple we applied to the structure to monitor the temperature during the manufacturing process, to monitor the increase in temperature due to the polymerization of the resin and the following curing process. I think you can see here that all the structure is closed by a nylon sheet. This was because we want to cool down the structure during the infusion process, because it was summertime. So the high temperature shortened the pot life of the resin. So what we did at those time was to rent a very powerful air conditioner. So we cooled down all the area around the girder during the infusion process. Once we manufactured the girder was transported in the city center during the night and was installed using a single crane, but from one of the abutments in less than 1 hour. The last bridge we built in Gabon in 2014, in our opinion, sum up all the best practice we have identified in the last decade. This is where the bridge would be located, and you see you have here a stream, and the government want to exploit this stream to produce electricity. So for this reason, they create a little hydro plant, and this bridge need to cross this little dam here. For this bridge, we use a simple support solution, an open FRP cross-section with a reinforced concrete deck, hybrid glass carbon laminates, and was manufactured by Resin Infusion. Here you have some pictures representing some steps of the manufacturing process of these girders. You see here, you see the dry fabric layered on the mold, and you see all the vacuum line here, and here you can see what are called resin infusion consumables. This is a peel ply, and this is the resin infusion media. This is a sort of net that is used to distribute the resin from the injection point all over the dry fabric. Here you see the vacuum bag, the injection point, just before the resin infusion starts. And here you see the curing process. The mold is covered by this blanket that is core is made by rock wool, and all the volume under this blanket is heated up by electric heater to a predetermined temperature to cure the girder. You see some imaging of the installation. You see that, as I told you, this is, in our opinion, the best bridge so far we have produced. The bridge superstructure is still free. We have FRP shear connectors, FRP reinforcement, and FRP stay-in-place formwork. Then I want to show you some other example of things we have done using composite material here in Spain that are not FRP girder bridges. And this is a pedestrian bridge we built in Cuenca in 2011. This typology is called stress ribbon footbridge, and is main resisting mechanisms or main resisting elements are this carbon fiber cable, which supports a very thin reinforced concrete deck. The footbridge has 3 spans. Each of these spans is 72 meters. And as I told you, the cross-section is formed by 16 carbon fiber cable that have a diameter of 42 millimeter and a 25 millimeter reinforced concrete deck. I forgot to tell you why the reason was behind this demonstrator, that cables represent an optimal way to use FRP, since they are mainly subjected to tension stresses. So in this, this was a project where our main objective was to test the behavior of carbon fiber cables. Carbon fiber cables, the carbon fiber cables we use are manufactured in this way. You fix 2 steel rings at the relative distance that is equal to the final length of the cable, and you start winding toe brake around this steel ring. So you have a machine that takes toe brake and goes like this around these 2 rings, this way. Then, so you have 2 bands of FRP. The following step is that all these 2 bands are wrapped with a thermo-shrinkable film. The film is heated up, so it shrinks, and you shape the cables. You give the cables this round shape. And close to the end, what you have, you insert here a polyurethane wedge. Here, there is a polyurethane wedge. And then you wrap carbon fiber around the cable core. You create a sort of a carbon fiber sleeve for a certain length close to the end of the carbon fiber. These carbon fiber have some drawbacks the first drawbacks due to the manufacturing process is that the length of the maximum length of the cable is fixed by the length of the machine, or if you want, of the workshop. The maximum length you can put between the two rings is the maximum length that the cable can have. So for this reason, you are forced to join cables to cover the entire length of the bridge. And the second drawback is that this cable must be transported straight, because once you consolidate the laminate, so you get the resin cured, the cable is very difficult to bend the cable. You have to transport it straight. So the transportation starts to be very complicated. In this case, we use, for this footbridge, 42-meter long cables. We perform some tests on these cables, because these cables are normally used for sailing boats, but for sailing boats that have a very small diameter, such a big cables hadn't been tested before. So before using them, we decided to perform tests. You see a tensile test, and you can see that the behavior of this cable is linear elastic till to the failure. This is the curve in terms of load displacement, and this curve represents the load and the strain measured at mid-span of this cable. So the behavior is perfectly linear elastic. The failure always happens at one end of the cable, generally in this region, that even if you model the cable using finite element, you see that the strain here are very high, and this was the conclusion of this test was that for sure is a good idea to use a cable, because this part of the cable works in tension, composite works in tension, and FRP has very good in tension. But we forgot that the problem you have here at the termination, where the cable suffer due to the fact that the fibers must go around the ring, so they have a curved configuration. So, as I told you, since these cables have a limited length, you are forced to join them. And the solution we use to join this cable is the solution that was used century ago for the first suspended bridges in the UK, which you have this chain you have made by plates joined by bolts. In this case, you have cables, and here they are joined by bolts. Conclusion. What we think that FRP girder bridges can be feasible candidates as future bridges in the span between 20 and 50 meters. Because they, as I show you during the presentation, they possess characteristics such as durability and rapid installation. Often I see people that try to apply FRP bridges for very long span bridges. From an economic point of view of a contractor, this is not very interesting, because large part of the bridges around the world has the span between 20 and 50 meters, a large part of the stocks. So it's very interesting to try to apply FRP to this range of span. Bridges have a span, very long span, around over the 1 kilometer, for example, are very rare. So from the point of view of a contractor, actually is not very interesting. So based on our experience, the best solution for this kind of bridges are summed up here. So they are FRP girder manufactured by Resin Infusion. The girder supports a concrete deck. The concrete deck is cast in place using collaborative. We haven't developed this concept. This should be very interesting. Using collaborative stay in place glass fiber formwork manufactured by pultrusion. This would be a future step. So far are produced by Resin Infusion and reinforced with FRP rebar. Another thing you have to test is the possibility to speed up further the construction process using abutment made by FRP mechanically stabilized earth wall. We have tested FRP mechanically stabilized earth wall here in Spain, in one of our sites, but so far we haven't tried them in the real environment, let's say in a real project. I take a chance to, I know that all this presentation will focus on bridges, but I would like to spend a couple of minutes presenting you some other structure we designed, manufactured, and installed using FRP. This is the last structure we installed last year in the port of Valencia. It's a 32-meter high fully FRP lighthouse. The columns are made of carbon fiber pipe produced by pultrusion. The floors here are glass fiber sandwiches manufactured by Resin Infusion. Here you have these stiffening rings are made by glass fiber pultruded pipes, and these slabs made by carbon fiber laminates produced by Resin Infusion. And this spiral staircase here, the steps are made by a sandwich structure made by polyurethane and glass fiber produced by RTM. It was a very interesting project. And I think we were awarded by GEC award this year in Paris. We received the award next March in Paris. This is another application for a high-speed train here in Spain. The main problem here, there were heavy water filtration in the tunnel. So here the solution was to create this corrugated FRP panel that can drain the water to the gutters that are located at the base of the tunnel. And is here the main challenge here was the fact that to comply with the 5 requirements in railway tunnel was very difficult. These panels were manufactured by pultrusion. And here you see another application here in Canary Islands. The prolongation of this jetty using 2 glass fiber caissons that was filled with sands, and they work as dolphins for the mooring system of the ships. These are the last 3 applications of FRP here in Spain we participated. I finish, I hope, this brief presentation of FRP application in Spain was interesting. And if there are any question, I'm happy to answer your question. Thank you very much.
Thank you, Carlo, for this very nice presentation. So maybe we can ask them in the chat area, or maybe you can ask them if you have a microphone. I don't know.
Yeah, there is a question here from Abzadeh. Okay, can you comment on environmental durability of glass used for bridges? And furthermore, glass is not good under fatigue load in bridges. Okay. Glass used for bridges in terms of durability. I think it's a good solution, glass fiber. If you go to desalination plants and chemical plants, glass fiber is massively used because it's the only material at a reasonable cost that is able to resist to harsh environments that you have in desalination plants and in chemical plants. And if you refer to UV protection, for sure you need to apply UV to your glass fiber element. But this is not a very complicated issue for glass fiber. Concerning the use of glass fiber under fatigues, we have performed tests on fatigue, on a reduced scale model of the girder, and what we observe is that actually it don't have a critical issue concerning fatigue for bridges. We didn't observe this in our tests.
Yeah, thank you. So another question. You can maybe ask them using your microphone, but based on what conditions you choose GFRP for the top flange and web?
The reason is that GFRP is the objective of a private company is to sell these girder bridges to the market. So they have to be sufficiently cheap to compete with concrete and steel solution. So far, GFRP is still much cheaper than carbon fiber fabrics. So you should try to use carbon fiber where is actually needed. And as I told you, the design of the FRP girders is dominated by the service limit state to the seg of the girder, especially under sustained load. For this reason, we use mainly carbon fiber in the bottom flange in the longitudinal direction, and we use concrete to resist compression. And generally in the web you can work very well with glass fiber. It is not an issue resistance due to shear stresses in case of glass fiber. And the top flange, we use carbon, we use glass fiber. Because if you try to perform a numerical analysis and look the compression strength of a UD laminate, considering the first ply failure between a UD laminate made by carbon, a UD laminate made by glass in pure compression, it doesn't pay to use carbon in compression. For this reason, the top flange that, as I told you, is in use only during the construction phase, because in a service condition actually is not loaded because the compression load are resisted by the concrete deck.
Okay, so thanks, Carlo. There is, I think that I agree completely on the fact that using carbon because of shear and cost is mainly quite
cost
a difficult issue.
Yes, the cost is the main issue.
There is another questions. Maybe Raphael want to speak or ask questions. Raphael, you raise your hand.
Thank you first for the presentation. And the question I have is related to that cable bridge. How did you guys address that type of the exposure failure of the cables, and how is it to do the maintenance and to verify if, for example, the strain or the stress on the cables are still in an acceptable range, because this is the main support of the concrete deck of that bridge, right?
Yes, the mainly support are these cables. You see, the failure is actually explosive, and what we did, and when during the installation we installed strain gauges on if I remember 8 of the cables, and we checked the evolution of the strain of the cables during the installation process and in service. This is the way we how we manage use these cables. And one of concern was mainly the creep of the cables, but so far we haven't observed so much creep in this cable.
Okay, thanks again for the response. Thanks. And maybe the last comment or questions coming from Gregory for it's complex questions about the price to try. Since it is prototype,
yeah.
I think it's...
No, I can tell you the cost is not actually a problem. It depends on the country. Depends very much on the country. In Spain, so far, for example, you cannot compete with concrete in short spans unless you have very complicated logistics. Sometimes, if you have logistics that is very complicated, the costs of saving very powerful cranes is compensated by the higher costs of materials. But in the short span, generally there is no competition with concrete. With steel, we are more competitive. I can tell you that to have you an idea, the cost of the deck or the cost of the superstructure of one of these bridges can be in the range 800, 1,000, probably close to 1,000 euro per square meter of deck. This is the cost of one of these solution. And probably is still higher respect of the cost of steel if you look at the initial cost of the bridge. But if you take into account the entire life cycle cost of the two solutions, you have a surprise, because you have to paint many times your steel bridge to maintain it, while this is not necessary with the same frequency for the FRP bridge. So if you have a solution with the FRP bridge, a concrete deck reinforced with GFRP rebars, from a life cycle point of view, is much better than a steel solution, even if the initial cost is a little bit higher.
Okay, nice. Thanks again for your very nice presentations. It seems that we don't have any comments. I would like to thank you, Carlo and Akshana, to share all these informations with us today. The next webinar will be on 26th of February about FRP confinement. So I will be pleased to welcome you again in this session. So thanks again, Carlo. And this webinar will be recorded. I have to work on it, but it will be we record and upload on the YouTube channel of IIFC, so that you can share this with a colleague or students, because I think that it could be very useful from some FRP community, scientific and also industrial maybe. So thanks a lot, Carlo.
Thank you very much.
Have a very nice weekend, and
you too. See you soon.
Bye.
Bye.